Well, heidi ho, neighbor. For those of you who are home improvement fans and used to watch Tim on Tool Time, his neighbor Wilson was kind of ahead of his time. This was the perfect way to social distance yourself in this time of quarantine. So Wilson just knew what was going on all along. But I thought I would kind of start out that way today just for some fun. And also because I decided to social distance myself from my beard for a while. Been a while since I've not had a beard, but I thought it's time to give my face a break. I don't know if I like it better, but it's something different. Just something to make me feel like I did something special on spring break, right? Hopefully you found a way to do something that made you feel special too. But afraid that time's over. We got to get back to some work. So let's see what today's lesson holds for us here. Hey, before we get started, I want to let you know this week office hours. Generally, I try to be online 10 to 11:30 in the morning. Be online for video chatting, questions, anything you got, problems you're having. We can work through them together online. Monday will be different. I will be on in the evening. I'm looking at 6 to 7:30. There will be a posting on Google Classroom with a link. You can click and it'll take you right to my chat room. So look for that on Monday. I'll be, and I'm trying an evening for Monday, and we'll see how that goes. So 6:30 to 6 to 7:30-ish probably. If it changes, just look for the link. It'll be right during that time. Most of the time during the rest of the week, I'm here in the mornings at 10 to 11:30, somewhere around there. But if it changes, just check on Google Classroom. It won't be earlier than that. I would do it later, so I wouldn't surprise you by you missing it. And then Friday, we'll have something a little different now. We're kind of changing since we're going to be doing this longer. We're going to be having lessons on Monday, Tuesday, whichever day is your A or B day. Wednesday, Thursday, and then Friday is just kind of an open day where you can get help, and we'll be online longer. Mrs. Smith also has office hours posted on Google Classroom, so you can click on there, and she's got some tutoring time she's looking at, but you can click on her link as well and visit with her with any problems or questions you have. Either way. So, today's lesson. All right, here we go. Let's see. We've got lesson 11 now for perpendicular lines in the plane. So let's get to it, geometry folks. Revisiting transformations. We remember transformations. The image shows quadrilateral ABCD. There's the 4 points of ABCD. Apply the transformation rule. XY becomes negative YX to quadrilateral ABCD, and what is the effect of this transformation rule? All right, so to do that, the easiest way is let's get the points. This D is on point 1, 2, 3, 4, 5, 2. All right, so D is 5, 2. I'm going to write that there. C is 5, 0. B is 5, negative 2. And A, of course, is at the origin 0, 0. Now, our rule says swap the X and the Y, and you'll make the Y a negative. So since that's supposed to be swapped and changed to a negative, let's take our rule for each of these. And this becomes negative 2, 5. Write that bigger, don't I? Negative 0 is still 0. This is negative 2 already, so it becomes positive 2, 5. And, of course, 0, 0 stays the same. So our new A is still A. B becomes 2, 5. It'll move right there. C becomes 0, 5. Is that right? Oh, no, this is 6, 0, 6. Man, I'm going to get a star for that, right? I did that as a 5. It's a 6. 0, 6. It didn't look right. 6, 0. And D is negative 2, 5. Now the new D prime, as it were, right? So this is B prime, C prime, D prime. And A prime are the same point. 0, 0, 0, 0, still 0, 0. So let's connect our points here. I'm going to use my ruler so I get that to be somewhat straighter than I do a lot of times on the screen. So there is our transformation now. What is the effect of this rule? What did this rule do? Looks to me like it is a rotation 90 degrees counterclockwise around the origin, right? Around that point. That's the point it rotated around. We have a 90-degree counterclockwise rotation around the origin. Nice. So that's what that rule does. When we swap the x and the y and we make the y a negative, that ends up a 90-degree counterclockwise rotation. Fabulous. All right, so let's look at what else we have down here. So this says, make a conjecture. We're going to complete the table with the slope of each segment from this warm-up up top. Slopes. All right, that takes us back to algebra. We can do that. These are all straight lines, right? So the slope is the change in the y over the change in the x. It's the rise over the run when we have it on a graph. Unfortunately, we have this lovely graph here that makes rise over run very, very simple. So our original figure slope for A to B. So AB, that would be this line right here. All right, AB is that line. So what is our rise over run? The rise is actually going down 2. So it is a -2, and the run is 1, 2, 3, 4, 5. So -2/5. -2/5 would be the original slope. Now the image, now remember this is the pre-image. Remember in the transformation you have an image and you have the pre-image. So after the transformation, it became right here. Right, A to B prime, A prime to B prime. So that slope rise 1, 2, 3, 4, 5, and a run of 2. So it is +5/2. All right, let's do the rest of those, and then we'll get to this product column over here. So let's see, what do we got next? BC. BC is this line, and our new B prime C prime will be that line. So BC, rise 1, 2, run of 1. So 2/1, which is the same thing as just 2, right? 2/1, same thing as a 2. Let's look at B prime, C prime. So this one, we'll start on the left side, so we know it. The rise goes down 1, so it's a -1, and the run is 1, 2. So this has a slope of 2. This has a slope of -1/2. Because that's a 1/2, 1/2. All right, CD. Let's change for a different color there. CD is this one. So from D to C, -2, +1. So that has a slope of -2/1, which is the same as -2, right? -2. And here D prime to C prime, it goes up 1 and over 2. Rise 1, run 2. The changes in the y's, it went up 1. Changes in the x's, it went +2. So has a slope of -2, has a slope of 1/2. And finally, our last one, I guess I'm going to use a highlighter. I ran out of color, so they have from A to D, D to A, would highlight that, and that one there. DA or AD. So the slope of those from A to D would be rise of 2, run of 5. So this is a 2/5. 2/5. And over here from D to A, it goes 1, 2, 3, 4, 5, -5, and then 1, 2, +. So -5/2. If you like to do A to D and want to stay consistent with A to D here, you can always go +5, but then it goes -2. So +5 over -2 is still -5/2. Either way. But I always generally look left to right in slope. So whichever point is farthest left, I will use that as my starting point when I'm looking at rise over run. But as long as you keep your positives and minuses correct, you'll end up with the same thing either direction. So let's look at this last column over here now. Original figure, image, slope, and the product. So the product, if you remember, when we add two numbers, that gives us a sum. When we subtract, we get a difference. When do we get a product? Product is when we multiply. So if we multiply these two together, -2/5 times 5/2. Well, if you remember how to do that, multiplying fractions. That goes back a few years, huh? Multiplying, you just go straight across. So negative 2 times 5, that'd be negative 10. 5 times 2, 10. So what's negative 10 divided by 10? Negative 10 over 10 is the same thing as negative 1. So the product of those two numbers multiplied together is negative 1. Now, how about 2 times negative 1/2? Well, 2 is the same thing as 2 over 1 times negative 1/2. And you can put the negative with the 1 or the 2. It doesn't matter. Negative 1/2. The negative can go with either one. But this ends up with 2 times negative 1 is negative 2 over 2. Negative 2 over 2 is also negative 1. Here we have the same thing. We just have a negative 2 and a positive 1/2. So if we move the negative over here instead of over here, we're still going to end up with negative 2 over 2. That's negative 1 over 1. And we got 2/5 multiplied by 5/2, with this one being negative. Again, negative 10 over 10. So the product of all of these with this 90 degrees counterclockwise rotation, the product is always negative 1 when we compare the slopes. So the image in the warm-up is a 90-degree rotation of the original figure. So each line in the original figure is perpendicular to the corresponding line in the image. Perpendicular. So use slope calculation to make a conjecture about the slope of perpendicular lines. So if we go back and say perpendicular, did I notice that? Let's see. Let's do the yellow highlighted one. All right, I'm going to extend that line out farther on both of those. They are perpendicular lines. Hopefully it's not distorted on the way it's showing on the camera there. But this is a 90-degree angle. That is a 90-degree angle. And it's also true with this red, the two red lines here from A prime to B prime and A to B. That is a 90-degree angle. Any two lines that are the same lines in the two figures are perpendicular. They're 90-degree angles. The blue ones, they're not touching each other. But if we extend those, let's do that. Let me use the blue and extend those. We will see. All right, there is that one extended. And then if we go to this one, I'm going to do it where I can see it better. If we extend those out, we can see those are at a 90-degree angle. Those are at a 90-degree angle. Let's see if we turn that, we'll put the angle where we're used to seeing 90 degrees. That's a 90-degree angle. So all of these with the 90-degree rotation, the slopes are 90 degrees different from each other. So if we want to make a conjecture about the slope of perpendicular lines, looking at the slopes, those are what we call, I don't know if you remember the term, opposite reciprocals. Opposite reciprocals. 2/5, the reciprocal of 2/5 is 5/2. You just reverse the fraction. 2 and 1/2 are reciprocals. 2 is the same as 2 over 1. So if we reverse that, it's 1 over 2. So 2 and 1/2 are reciprocals. And the negative is what changes it to where it's perpendicular. So it's an opposite sign, opposite reciprocals. So if we use opposite reciprocals, slopes, we're going to have a perpendicular lines for opposite reciprocal slopes. We're going to write that down here. Opposite reciprocals. Sweet. That tells us a lot right there. So we see the equation. A lot of times we can know what the lines look like without graphing them, because if we see the slopes are opposite reciprocals, right away we know what it's going to look like if we put those two lines on the graph. Okay, let's move on and see what it wants us to do next. Let's prove our conjecture about the slopes of perpendicular lines for the case where the lines pass through the origin. Let's simplify it. Let's just take them through the origin. And we're going to try to prove our conjecture. Our conjecture is that the slopes are always opposite reciprocals, right? So find the slope of a line passing through the point AB, which could be any point, and the origin. Assume the line is not horizontal or vertical, because that messes things up because we don't have a slope of a vertical line. It's undefined because there's no run. It'd be divided by 0. So AB would be any point. Remember, it's the difference in the y's over the difference in the x's. So it would be technically the y's the second one, right? So B minus the point at the origin is 0, 0. Right? B minus 0, A minus 0. Well, that's the same thing as just saying the slope is B over A. From the origin, it's B over A. So that's our slope of the original line for the point AB and the origin. So suppose this line is rotated using this transformation, where we're going to take x, y, and we're going to reverse them, and we're going to make the y a negative. So let's find the coordinates of the images on the points A, B, and the origin. Well, the origin is still going to be at 0, 0, right? That's not going to change. If we switch the 0 and the 0, if you make a 0 negative, it's still just 0. But the point AB becomes the point negative B, A, right? So we took the y, we moved it to be the x, and we changed the sign. So that is the coordinates of the new images. So how does the original line relate to the image? So the original line would have been from origin to whatever AB is, and this one would switch it to where it should be over here. Should be 90 degrees counterclockwise rotation around origin. Right, it should move 90 degrees, and this was our origin. Find the slope of the image. So the image would be over here. AB would be over here, whatever that was, and this would be negative BA. So the slope of this now, we're going to find the slope of this line. So the y position is now A. Remember, it'd be like A minus the original point of the origin, and B, that point. So A minus 0 over B minus 0, which would just be, oh, wait a minute, B is negative B minus 0. So this would be the slope A negative B. So that is the slope of the image. How compare your slopes, and what did you just prove? The slope here is B A. That's the original line, the pre-image. Our new slope is A over negative B. Now, what did we just prove? Those are opposite reciprocals. We take the fraction, we reverse it, turn it over, and we make it a negative. If it's top or bottom is negative, it's the same thing as just a negative A over B. The negative can go with either the top or the bottom, so it's the same thing. So let's see, with our product that we used earlier, do they equal the same thing, negative 1, as the other ones did? If we took that times A over, well, I'll put a negative up front, B. So negative, I'm going to make these A's like this again because they're starting to look funny on me. So what's A times B? Well, that's just AB, right? And A times B, AB, and we have a negative that goes with one of them. So AB divided by AB, whatever A and B is still going to be negative 1. That shows right away that these are opposite reciprocals because the product is negative 1. That's what we found on the other ones. We were using actual points instead of just figurative points. These variables can be any points, A, B, but still it equals negative 1. That works out really nicely. So our next page is, are you ready for more? It says we can take any rhombus, EFGH, and well, let's say, what is a rhombus? Let's pull up an image. Rhombus is any four-sided figure where all the sides are the same length. So here's some examples of some rhombuses I'll hold up for you. Diamonds, parallelograms that have all four sides the same. So squares, these are all, well, that's a rhombus. Those don't necessarily qualify as a rhombus. A rhombus has to have all the same side lengths on all four sides. So that's a reminder of our rhombus. So we can take any rhombus, E, F, G, H, and we can translate it so that the image of E is 0, 0. So the first point right there, we can translate it so it will be on the origin. Right? We know we can do that. And then we can rotate using that as the center, using that origin as the center, so that the image of F, the next point under the sequence, is on the positive x-axis at some point, right? Whatever that point is, C, 0. So we can line it up where if it's a square or whatever shape our rhombus is, we can put this point on the origin at 0, and we can rotate F around to where it is also on the x-axis, right? It'll be at C, 0, depending on how far it is between E and F, will be the point C, right? So we can do that. So suppose these transformations take H, right, our other point over here, to some point AB. What must the coordinates of G be? Well, anyway, let's take this, put some graph paper here, and play with that idea. Let's start with, let's see, what shape would we like it to be? Let's say it is going to be a square. How about that? We can do that real easy because we have these got some bolder lines on my graph paper. So we can say, okay, we're going to take this square and we're going to say it originally started right over here, right? That was our square. Let me highlight that, make it a little easier to see. So that was our square, and we translated it to where we had point E right here. So labeling our points, this was E, F, G, and H. All right. If we take that and we translate to where this is now E right here on the origin, and F now would have to move to be right here. This would be F. So it is going to be at, it said C, 0 is what it said. Well, in our case, since our square has a length of 5, that's going to put that E is at 0, 0. So F is going to be at 5, 0, because that is the length of that side of the square. So now it's asking us, it says, suppose it also takes point H to AB. All right, so H is going to be right here, right? Because it also, so being a square, has a height of 5. 1, 2, 3, 4, 5. H, in this case, is going to be at 0, 5, which they're saying A, B. Because it wouldn't have to be there if our rhombus was not a square, but it still had all 4 sides. It could have been where F was up here and H was over here, so it wouldn't have to be necessarily on the y-axis, but using a square, that's what we end up with. So what does the coordinates of G have to be? So it said this was calling it C, 0, right? So we know G would be right here, which would be 5, 5. But that's specifically for this square. They're talking about for any rhombus, E, F, G, H. If C was 5, that was also 5. So the coordinates of that would have to be, this is G again, C, it has to be whatever F is for our square, and B for whatever the H is, because it's at the same height as the H. Okay, so in this case, that ended up at 5, 5, which is the same as CB. Now, this could be a special case because it's a square, so let's look and see a different rhombus, because we might be missing something by just using the square. It seems a little bit simplistic that it would just be CB. I think just because it's a square is what we ended up with. So let's say that we had a rhombus that had a distance equal to this. Okay, we'll go diagonally. And so that would be 3 by 3. 3 squared plus 3 squared equals C squared. So the length of that would be, since this is a 3 by 3 triangle, since this is a 3 by 3 right triangle, we can use the Pythagorean theorem to figure out how long that side of our shape is, right? So that's not part of our shape, but we're using that triangle to figure out the length. So 9 plus 9, so C squared is 18. So let's pull up a calculator and see exactly how long our side length is. So we pull up this calculator and we say 18, and we want the square root of that. It's 4.24. So just under 4.25. So the length of that is 4.2. We'll call it 4.25 just to round it off and give us something easy to work with. So since that is 4.25, then the length this way would put it about right there. And that would also put this about 4.25 there. So if we connected those, that is a rhombus. All right, all four sides are the same length. They're about 4.24, 4.25. We rounded it off 4.25 for just for graphing purposes. 4.24, putting it about right there. So we can translate this just like the last time, and we can make this. This is E, F, G, and H. Right. So we can translate this up here to where E is at 0, 0. And F would be right over here, F, and it's at 4. I'm going to use the 4.24 just to be more precise. 4.240. That is the point F. And then this went up to there, which would be 3, 3, right? So this is 3, 3, because that was just straight on that point. And this would go up, will be over 4.24 and up 3, 3 this way, over 3, up 3. 1, 2, 3, 4, so right there. And that would be 4.24 plus this, right? So this would be about 1, 2, 3, 4, 5, 6, 7.24, and a height of 3. So this looks a little different than our square did. With our square, C right here was 5, and so that was also 5. We said, oh, it's just equals what C is. But let's look at this one here. F was 4.24, but G, well, let's move right, G, H, is 7.24. It's not the same. So if this was C, comma 0, and we said this was AB, what is G? Well, to get 7.24, we would have to take C, the 4.24, and add A to it. So it's A plus C. Oh, not parentheses yet. Getting ahead of myself. And the Y would just be the same height, right? The Y is the same height. A plus C and B. So if we add the two X's together, however far they came over, it worked up here in the fact that the X was 0. So really it was 5 plus 0 equal 5. We just didn't see that because we had that 0. So this is actually A plus C also. A plus C. Okay, let's go back to what our questions were here. What must the coordinates of G be? They would have to be A plus C and the same height at B. Okay, interesting. So for the values of A, B, and C, why is it true that A squared plus B squared equals C squared? Well, because what we saw here, A would be this length right here, right? And B is the height. That would be the A and the B, because this is the point AB. So C would be that side, which we saw here. We had to figure out what that length was right there so we could move it right down here and make that point. All right, we did that to figure out how far F was. So that's the measurement we used to find this. So A squared plus B squared gave us C squared, so we could figure out where this point would have to be to make that a rhombus. So we can see that. Okay, so number 3 says, prove that the diagonals of the image are perpendicular. Okay, so let's talk about the diagonals. H would be the point AB, and in our diagram, E, F, G, H, the diagonal would be from H to F, right? That'd be diagonally. And then G to E would be the other diagonal. So these would be the diagonals either way. So let's figure out the slopes from those two lines. So the slope from H to F, if H is AB and F is C0, whatever AB and C equals in those equations, E we know is 0, 0 because we translate it to be the origin. And G we decided was A plus C B. So the H to F, looking at the difference of the Y, be B minus 0. So just B. And the X's would be A minus C. That would be the slope from H to F. B minus 0, the difference in the B's, and A minus C. The slope of the other one, because we may multiply them. We need to multiply them, see if they're perpendicular. See if we get that -1 product, right? So for E to G, the Y's would be B minus 0, and the X difference would be A plus C minus 0. All right? So the difference, B times B is B squared. This would be A minus C, it would be A squared minus C squared. Okay, so far we're looking at it and going, that doesn't look like a -1. But when we go back and look at this statement, A squared plus B squared equals C squared. So if we go back and we substitute in for C squared, A squared plus B squared. All right, so for this right here, we're going to say this equals B squared, A squared minus, and then what we substituted in for C squared was A squared minus B squared, right? That's what we substitute in for C squared right there. That's all we did is substitute. So A squared minus A squared is 0. B squared over negative B squared, negative B squared, well, it is -1. Okay, now it says prove that the diagonals of the image bisect each other. So the diagonals bisecting each other. Well, that means they'd have to have the same point in common. They bisect each other in the middle. So let's find the middle point for each line. E to G. So we would add the x's together and divide by 2, and that would be halfway. And then same thing with the y's. That will give us the point that's the middle of that. A plus C plus 0. That's just A plus C, and we divide it by 2. That would be the x, and the y would be B plus 0, which is just B, divided by 2. Okay, so that is the midpoint from E to G. That's the midpoint. The midpoint from FH is the C. The x is A plus C divided by 2 would be the middle up and left and right. The middle up and down would be the middle between the y's, which is B plus 0 divided by 2. B plus 0 again. Well, there you go. A plus C over 2, B over 2 is the midpoint for both lines. So the diagonals have the same midpoint, so they must bisect each other because that is the middle of both of the diagonals. So that's the middle of both of them. They must cut each other exactly in half. Why does this imply the diagonals of all rhombi are perpendicular bisectors of each other? If we know they bisect each other, which we see right here, because this is for any rhombus, right? We didn't give a specific rhombus. We left the points anonymous. It could be C and A and B. Those could be any points for any rhombus. So those diagonals do bisect each other to cut each other exactly in half. And using, again, those same variables, we find that the slopes are perpendicular slopes. So since they're perpendicular slopes, and they bisect each other, they are perpendicular bisectors. All right. We are through with that lesson. We've done plenty. I will have the summary online. You're going to go back and look at it. It's wonderful. It shows a nice illustration of the perpendicular lines, looking at the slopes. It's all on one page. It makes it a lot simpler if you want to look at that. Otherwise, you'll have an assignment, some problems to do. Remember, some of the problems are about this. It also has some problems that review stuff we've done previously, because it is cumulative problems. It's not just over today's lesson. It keeps you refreshed on what we've learned before. You can always pause this, go back and re-look at parts of the video if you didn't understand something. I would encourage you to print out the blank notes that I attach with the video, so you can do it as I'm doing it, or you can try to work it ahead and then stop and see the way I did it if you get lost. And if you need help, I will be online, live, video chatting. And don't forget, we're online. Mrs. Smith and I are both online at different times, or sometimes even overlapping times. But we each have our own video chat room where you can get help. So if you're having any trouble with any of this, please check with us. And I hope you're having a good time doing this online, not having the distractions of school. Hopefully you've got yourself a place where you're working and can focus on your work and get it done, and not have to spend 7 or 8 hours like you are at school. You can wrap it up in less time if you're focused and just concentrate on your work. So do work you can be proud of. Have a good day.